Okay, coming back to our Chapter 3 videos, and we're picking up talking about Avogadro and the mole. And although this may sound like the title of a children's story, it's not. But it could be. It's going to be a very fun science-related children's story, but alas, we are doing chemistry here, so less fun. But anyways, so Avogadro was a very famous Italian mathematician, and he established a counting unit that relates to very, very, very large quantities. Okay, and what he called it was the mole. Okay, and the idea is that Avogadro's number is a mole of something. Okay, so a mole is a counting unit. Not units, unit. Okay, so other counting units that you may be familiar with, things like 1 ton equals 2,000 pounds. That's a counting unit. When you get to a large enough quantity of pounds, it's more practical to refer to it in a different unit that sort of makes it a smaller thing to deal with. Instead of saying 4,000 pounds, we can just say 2 tons. Okay? Avogadro's number says that 1 mole of something equals 6.022 times 10 to the 23 of whatever that thing is. Okay, so this can apply to anything, really. Okay, I can talk about a mole of cars, a mole of leaves on trees. I can talk about a mole of marbles. It's just a counting unit. If I say that I have a mole of something, that means that I have 6.022 times 10 to the 23rd power of that thing. Okay? In our case, we're going to primarily refer to atoms, particles, molecules, things of that nature. Okay? But I could talk about, like I said, a mole of cars, or a mole of couches, or a mole of computers. It really doesn't matter. It's a counting unit just like any other counting unit. What's useful to us about it is that we can use it as a conversion factor. Okay, we did all that stuff in the previous chapters where we were converting units and transforming things from one unit to another using conversion factors. We did that with density. We used density as a conversion factor. Well, now we can use Avogadro's number and the mole as a conversion factor. So I can write that as 1 mole of something is 6.022 times 10 to the 23rd of that thing. Or 6.022 times 10 to the 23rd of whatever I'm talking about in 1 mole. Okay, it works as a conversion factor just like any other thing. And we're going to use it to find out how many of something. And I say it in those terms because a question that I often get from students is, how do I know when I need to use Avogadro's number? And the question is, or the answer to that question is, whenever you're being asked to determine how many of something, how many atoms, how many particles, how many molecules, that sort of thing. Or if you have a number of something, say I have 6.02 times 10 to the 23rd atoms, and I want to find out how many moles that is. Okay, so whenever I have to go back and forth between a counting number and moles, okay? So the how many of something is a key phrase in a lot of these questions. So let's do an example. Our question says, how many atoms are in 1.25 moles of hydrogen atoms? Hydrogen atoms. Okay? So I'm going to treat this just like any other conversion factor problem. Okay, and the reason that I do it this way is so that you only need to think about one way to approach your problems. Your chemistry problem, that is. Your life problems are your own deal. But I'm going to start by writing down my given information. Okay, just like when we did dimensional analysis with unit conversions, I'm going to start by writing that given information. Okay, and the abbreviation for moles is just MOL, so you'll see that quite often. So 1.25 moles of hydrogen, and I'm going to use the conversion factor that cancels out the unit moles. Atoms of hydrogen in 1 mole of hydrogen. Okay, so you can see the pattern is the same as when we were doing simple dimensional analysis. Moles of hydrogen go away, and I'm left with a unit that is atoms of hydrogen. And the answer will be 7.53 times 10 to the 23 atoms of hydrogen. Let's do another example. How many moles of ammonium atoms? Ammonium ions are in 9.4 times 10 to the 24 molecules of ammonium. Okay, so I'm going to do the same thing. I'm going to start with my given information. 9.4 times 10 to the 24 molecules of NH4+. And I'm going to use a conversion factor that puts molecules on the bottom and moles on top. So I have 6.022 times 10 to the 23rd molecules of NH4+ in 1 mole of NH4+. Okay, so Avogadro's number can apply to any item. I can talk about molecules, individual atoms, generic particles, whatever I need. Okay, as long as I'm talking about relating a counting number to moles, that's when I know to use Avogadro's number. And so in this case, my molecules of NH4+ will cancel out, leaving me with an answer in moles. And when we do that calculation to the correct number of significant digits, we come out with 16 moles of NH4+. Okay, now, how do I know it's only 2 sig figs? This is a definition. Okay, so this relationship of Avogadro's number to the mole has infinite significant digits. Okay, it's an exact number because it's a definition. So when I want to determine sig figs for a problem like this, I look at my initial information, which has 2 significant digits. So now, let's take a little pause from what would actually come next in the notes and back up to a topic that I probably should have talked about in Chapter 2, which is the idea of molar mass. Okay, so we get molar mass from the relationship to moles. That's why it's called molar mass. Okay, so when we look on the periodic table at an element, let's say I'm looking at sodium, and the number below the symbol for sodium is the atomic mass, the average atomic mass. And when I look on there, it says 22.99 AMU, atomic mass units. Okay, through the relationship of atomic mass units and moles, it's the same thing as saying 22.99 grams per mole. Okay, and what that means is that 1 mole of sodium atoms has a mass of 22.99 grams. Okay, so the number on the periodic table in AMU is numerically equal to the mass in grams per mole. Okay, so if I want to know the molar mass or formula mass, okay, if I'm talking about formula, I'm probably talking about a compound of something like CO2. Okay, I'm going to look on the periodic table and find that I have carbon is 12.01 grams per mole. Oxygen is 16 grams per mole. Okay, and when I want to know the formula mass for this whole molecule, I have one carbon atom and two oxygen atoms. So I'm going to say 1 times the mass of carbon plus 2 times the mass of the oxygen. I literally add up the masses of each atom in the formula in grams per mole. So we should come out to be, what is that, 44.01. for carbon dioxide. Okay, so I'm going to go ahead and stop this video right there, and we'll come back next and talk about how moles relate to formulas and chemical equations.